All right. So today's lecture is about lattice field theory. Specifically, that means a discretization of field theory in a consistent way, such that we recover the continuum. In the continuum limit, we recover the true field theory. Somebody wants to be in, okay. The reason for that is, of course, that we want to do computer simulations. Until now we have described perturbative methods to deal with quantum field theories. Well, we also have talked about something that is kind of non-perturbative but is fixed from experiments, like Barton distribution functions and so on. But for true non-perturbative physics, we have few tools, and one of them is, I mean, the most complete of them is simulations, computer simulations on a lattice. So we have, in this way, we have a finite number of degrees of freedom. So you can simulate it, and we do Monte Carlo simulations, meaning sort of random scan of the parameter of the coordinate space for the path integral of the coordinate space for the action. And we will start with the continuum limit related to the Kadanoff blocking from the last time, since last time we also considered a theory on in discrete points in space-time, and only in that case we thought of it more like condensed matter theory. This way we want to find the continuum limit because we know that there is supposed to be a true field theory in the continuum limit, which we're after. Okay, so the important result that we'll consider is that the critical point is independent of the particular normalization group procedure considered. So the normalization group procedure from the last time was Kadanoff blocking. Here we will use this lattice kind of RG procedure. And we saw that we had described everything in lattice units. I mean, we considered dimensionless quantities, and we considered S units of the lattice, but we didn't think of the we sort of threw away the lattice size A. But in order to get to the physical quantities, we have to reintroduce the lattice spacing A. So for a coordinate, for a physical coordinate x physical, we'll have this lattice number xl times the lattice size A, and also for the for psi, we'll also have psi physical is xil times A, and momentum physical is PL divided by A. So we want physical quantities like this correlation length psi to be the physical ones to be fixed, but the new thing with respect to last time is that now we consider the lattice spacing going to 0. So before we had the finite lattice size, and then we do the blocking, meaning averaging over a number of sites. But the procedure now is to keep physical length and momentum quantities fixed, and take the lattice size to 0, since really that's what we want to do in order to reproduce. That's what it means to have a continuum limit for obtaining a field theory. And so we do that by replacing A with A over S under the RG action. And that is done instead of the procedure that we did in the second part of last lecture, when we took beta going to beta C. There was a so we had a renormalization group action on the betas, beta n going to beta n plus 1, and so on, that went to beta C. And then, so here we talked about correlation lengths psi, but if I think of psi as some other coordinate scale, then there's a physical mass scale that is one of the coordinate scale. And all of these mass scales and coordinate scales will be fixed when we take A to 0. But to get to the continuum correlation functions, we need to also make a wave function renormalization of them, meaning these correlation functions in the continuum, depending on the physical masses and momenta, is the correlation, the lattice correlation depending on these PLs and parameter scale of A, but multiplied with A to the minus the anomalous dimension, and then take A to 0. So the point is that only A varies, and A varies because, and the multiplication is only with the anomalous dimension, because the physical one is already included. I mean, this is supposed to have the physical size. So G goes to 1 over x to the delta classical plus eta. So next, let's understand the Gaussian fixed point. Under the RG transformation x going to x over s, since if we take a classical field, it's a classical scalar field, its dimension is d minus 2 over 2. So that means that phi s of x over s is approximately s to this classical dimension. Classical dimension d minus 2 over 2 times phi of x, right? That's assuming the classical dimension in phi. But then we find, so the term in the action will be the coupling kn times the integral d dx times phi to the n. And then the scaling of kn with s, kn go to s minus dn kn, results in this dimension dn, which is the classical dimension of the coupling kn, is minus d minus 2 over 2 n plus d. I mean, this comes from phi to the n, and this comes from d dx. But then, so the RG transformation from last time, we described it last time as a motion in parameter space. And that motion in parameter space could be diagonalized. We find eigenvalue and eigenfunctions, or eigencouplings if you want. And well, apparently Kn is an eigencoupling, and then its eigenvalue is this, s to the minus dn. So then, for the Gaussian fixed point phi equal to 0, we obtain the same analysis that we had in quantum field theory 1, that relevant operators, which last time we defined the ones with lambda n greater than 1, are the ones that have, so lambda n greater than 1 means dn negative, right? So that this is a positive power here. And dn is the dimension, the mass dimension of the coupling Kn. So relevant operators have mass dimension negative. And that means super normalizable. Irrelevant operators have lambda n, from last lecture, have lambda n less than 1. But then that means the mass dimension dn is positive. And then they're non-normalizable. And when lambda n is 1, that means dn, the mass dimension of Kn, is 0. So then they are marginal operators, which means the theory is renormalizable. In particular, as we know, in 4 dimensions, lambda phi 4 theory has massless dimensionless lambda. So that means lambda is a marginal coupling, which means that we need to go to higher orders to see whether it is relevant, irrelevant, or exactly marginal. And as we already described, relevant or super renormalizable operators are UV asymptotically free, right? In the UV, the couplings go to 0. And the irrelevant or non-normalizable operators are IR asymptotically free, meaning the coupling goes to 0 in the IR at large distances. But for these latter ones, the non-normalizable and IR asymptotically free, at the Gaussian fixed point, when you take the bare coupling to 0 in the IR, the renormalized coupling goes to 0 even faster. So it seems to be impossible to define a theory with non-zero physical coupling at large scales, which would be non-trivial. So that's another way of saying the fact that we've described several times, that lambda phi 4 and QED, which is also of this type, whether they're a theory that actually makes sense from a non-perturbative point of view. I mean, perturbatively, they're great. It's easy to calculate, and things are matching very nicely with experiment. But in the non-perturbative sense, it is not clear. There is the possibility that there are other fixed points where one could define the theory, and then this Gaussian fixed point would be a derived point of the theory, non-perturbatively defined around another fixed point. So there's a lot of debate about this. I mean, people usually don't think about this because you do just perturbative calculations, but from the theoretical point of view, it's a big debate. On the other hand, as we know, UV asymptotically free theories have no problems, since we can always keep fixed and normalized coupling in the IR and obtain a non-trivial interacting theory, while in the UV, the couplings go to 0. So in the IR, because we live in the IR, that's the point. We are at large distances. We see large distances. We don't see small distances. Beta function, the beta function. All right, so this RG procedure that we're describing now, in terms of A goes to 0, allows us to define the beta function in another way. If we rescale the correlation length by S, so psi, well, psi prime, I should say. I don't know. Well, yeah. If you think of psi as a function of G, then let's say psi at G prime squared is S times psi as G squared. So psi of G squared is a function here now. But the couplings in this case must be changed. I mean, if we multiply by S, then the coupling has to be changed. G prime squared is G squared minus delta G squared. However, we want the long distance physics to be unmodified by this rescaling procedure. So that means that we also need to rescale A. So A then should go to A over S, right? So the resulting yeah, so psi is, we said here, psi physical was a psi times A, psi L times A. So if A goes to 1 over S and psi L goes to 1, well, psi goes to S psi, then the physical ones are unchanged. But that means that we define also an A implicitly by these two relations. We also find an A of G squared, a function as a function of G squared. So A of G prime squared is 1 over S, A of G squared. Or reversely, we find that there's a coupling that depends on A, G of A. So after n blocking steps, after n going to infinity blocking steps, you should always be on the same RG trajectory, independent on S or independent on the blocking or type or anything, right? So because the long distance physics is supposed to be the same, that's what we're after. We want that the long distance physics, the X physical and physical and so on, should be all the same. So that means that all of these blockings with different S and, well, different procedures perhaps, should asymptote to the same RG trajectory. So for the RG trajectory in terms of coupling, so here is the coupling G squared that we're looking at, and here are other couplings. And this is the RG trajectory, the asymptotic RG trajectory. then these blockings, which are discrete jumps, these various blockings should asymptote to the same RG trajectory. All right, but so we've just saw that we've defined, in this way, we define a function a of g squared, or reversely g of a, so coupling depending on a. So that allows us to define an alternative, the beta function in an alternative way. So beta of g is now minus a dda g of a. The minus is because before we had lambda dd lambda, right? Lambda is a momentum scale, a is a coordinate scale, so this is d log a, which is minus d log lambda in some sense. All right, so in some sense, but this definition is really not the original one, because the way we define things now is with respect to this rescaling and blocking and so on. So that's a different definition than the usual one. However, we can prove that the first two coefficients in the expansion of beta of g are the same. And of course, the fixed points are also the same, since you know, this the asymptotic RG trajectory goes to the fixed point. So okay, so these were the preliminaries. But now let us define lattice gauge theory. So lattice gauge theory will be defined in terms of these discretization and with the limit a goes to 0, because that's really what we think of as the continuum limit for obtaining a field theory. So the theory of interest is QCD, which is a non-perturbative gauge theory in the IR. So it's UV asymptotically free, and in the IR is non-perturbative. So in the IR, meaning at low energies, it's very hard to calculate anything. The only way we know to calculate exactly in QCD, I mean, there are other models that give, I mean, phenomenological or otherwise, or ADS-CFT ones, or but they are all approximations of QCD. So in QCD itself, we only know how to do this on the lattice. If we consider a gauge group G, then the gauge theory meaning local gauge that has local gauge invariance, then at each point x there's this group G. So in some sense we can have a global group that is the product of all the groups G at x. Well, all the x belongs to R to the D, so to all points. Now, of course, in the discrete case, it's not R to the D, but really the lattice. So there's a global group that corresponds to the product of the groups at each lattice point. Now, we can we saw that we can define an observable called the Wilson loop. We've described it a few lectures back. That is, so the Wilson loop is trace path order exponential of I times the integral over a closed path C of A mu dx mu. A mu is A mu ATA, and we can parameterize the contour C by a parameter t from 0 to 1, as C, depending on t, is the function that takes t to x mu of t. Then the trace of the Wilson line you see for a closed contour so we have the trace of a Wilson line you see. So you see tilde is the trace of a Wilson line you see in the case of a closed contour. But then you see in here satisfies composition, meaning that the total you see, if you divide it into portions, into steps, C1 up to Cn, it's UCN, UCN1 up to UC1. And then UC of T. So if we parameterize it by this parameter T, is the limit when n goes to infinity of the product, so such a product. And for an infinitesimal one, in here we have exponential I dx mu times a mu of x. But x now is discrete, so we think of it as x xk. So dxk mu, and here a mu xk. We also saw that the Wilson line transforms covariantly, meaning from one side, UC of t goes from one side, from the left, to with the parameter, the gauge parameter v at point x of t, and from the right with v at the point x of 0. Okay, so if UC of t is from 0 to x of t, from x of 0 to x of t. And the gauge transformation is with parameter v of x, meaning a mu goes to v of x, a mu of x, v of x at -1, minus I d mu v of x times v minus 1. Again, we saw that in the abelian case, we can use the Stroke theorem to write this thing in the exponential. So the exponential was of I integral of a closed path C, a mu dx mu, as exponential I over 2. Yeah, here it's missing the integral. Right? Well, okay, I presume, sorry, yeah, I presume in this case, I wanted to write the infinitesimal surface, dA mu, bounded by the infinitesimal contour C. And then that's why I didn't write here integral. Normally, would have been in the Stroke theorem, there's an integral of a surface equal to the integral of a boundary. But here the surface is infinitesimal, so then I just wrote dA mu nu times the field f mu nu. But in the non-abelian case, we have corrections in the exponent. So the non-abelian case, we have to have, first of all, path order exponential of the same thing, I integral over the contour C of a mu dx mu. And then in the exponent, we have the same I over 2 f mu nu d a mu nu, but then plus higher order corrections. corrections of order dA squared. And then by taking the trace in order to obtain the Wilson loop, and then the real part, and expanding in the exponential, the real trace of this thing. So exponential starts at 1, or the identity, since this is a matrix. So the first term here is trace of the identity. But then the second order term will be minus 1 over 8 trace f mu dA mu squared. So the first non-trivial case. So because the first order term is I over 2 trace I over 2 f mu dA mu, but that is 0 because that has trace f mu, which is proportional with trace TA, which is 0 for the trace TA is 0 for the case of interest, which is SUN. So yeah, I should have said here. So for SUN, this is for SUN. So this is for SUN, because we're interested in QCD, which has the gauge group SU3. And then the only non-trivial, the first non-trivial term is the quadratic term. So with f mu dA mu squared, the trace, now this is non-zero. The coefficient is minus, so it's 1 over 2 times this I over 2 squared, so minus 1 over 8. So we're finally at the point that we can define the gauge theorem, the lattice. We notice what we obtained here, trace f mu dA mu squared. Now, trace f, from point of view of trace, is really trace f mu squared. And that sounds like the action for Yang-Mills, or the gluon term in QCD. But then how do we obtain this from this Wilson loop? We have to get something that looks like a Wilson loop on the lattice. So on the lattice, we have sites I, and then there are also, we can also define the links that connect the sites, links ij. And then on them, we can naturally define an orientation. So we can naturally associate an element of G to each oriented link. So we define the group element U with indices ij, which means oriented from I to j, so belonging to the group G. And then this oriented, group that's related to the oriented link has the property of a Wilson line. Indeed, if we reverse the orientation and compose the two elements, we're back to the identity, right? So, I mean, we should get back to the identity. So that means that uji is u minus 1 ij, which is also what we would get from this infinitesimal definition, right? You go I dx mu, and then the inverse is with minus dx mu, which gives it back to the identity. Moreover, the gauge transformation is the same as for the Wilson line, meaning this link element under the gauge transformation transforms. So the gauge transformation, remember, is defined at every point on the lattice. So there's a global gauge group. You can think of being a total global gauge group. There's a product of the gauge groups at each lattice point. So that means I can define the gauge transformation V at point I. So we try the gauge transformation V in the whole space corresponds to gauge transformation, global gauge transformation at each lattice site. So there's a V at I. But since this is an oriented, it's associated with an orientation, this Uij, the transformation at the point J has to be with the inverse, Vj minus 1. So that corresponds to this this transformation law of the Wilson line. Now we can also define along a connected path on the links the analog of a long Wilson line by just composition. So we define the composition of these link elements. So U of C is, again, I mean, in the same way as we defined here. U of C is U of in minus 1, U of in minus 1, in minus 2, da, 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 up to U I3, I2, U I2, I1. Right? And then finally, for the Wilson line itself, I take a connected, a closed connected path, and I take UC, and I take its trace. And also, again, because of this transformation law, for the individual links, for the total one with the trace, we have a gauge invariant object, UC tilde. Okay. So we've seen that we've associated a link variable, Uij, that corresponds to the elementary Wilson line for the link. So it corresponds to this path order exponential of the integral of dx mu a mu of x. Where, so I have this path associated x mu of t, this path from x mu of 0 to x mu of 1. Or specific, or if I want to just for the link, just for one link instead of the whole path, then I have the path order exponential here is between x mu of I and x mu of j. So x mu of t is t x mu of j plus 1 minus t x mu of I, where t goes from 0 to 1. And so this link variable is associated with this Wilson line for the path between I and j. But the link variable is also associated with a point, with a midpoint, the point at t equal 1/2, which is x mu of I plus x mu of j over 2. Now, the smallest non-trivial closed loop so would be this, where all of these things, so a square like this, where all of these things are nearest neighbors. This would be called a plaquette. So a square with nearest neighbor vertices, and we can call them I, J, K, L. So P is I, J, K, L. And then since this length is A, the area is A squared. The area of the plaquette is A squared. Then from this relation that we found from the real part of the trace of the closed Wilson line, since we had this relation, then we find that trace I minus real part of trace U associated with the plaquette P, which is this smallest square, is 1/2 times the area squared. So d of dA is the area squared. Area squared is then A to the 4. Trace F mu nu. Mu and nu here are the directions on the plaquette. So this direction, let's say it's mu, and this direction, it's nu. All right. So yeah, this is, I'm sorry, this is 1/8. This is an error here. It's 1/8. Right, 1/8, trace 1 minus, yeah, it's 1/8. Okay. So that means that we can define from this relation, we can define the Young-Milled action for the plaquette. The Young-Milled action for the plaquette is trace F mu nu squared over 4. So this would be the Young-Milled action for the plaquette, and then we sum over plaquettes. And in order to obtain the action, what would correspond to as the action, the Young-Milled action in the continuum limit. So replacing, so we want to get this, but you obtain this here, and then sums over plaquette. So we see that to obtain the correct continuum limit, we must write from this form, from the Wilson Wilson lines associated with coming from links associated with Wilson lines. We get the so-called Wilson action, the action that was first found by Wilson, who first defined this lattice field theory for the gauge theory and the lattice. So the Wilson action is this one, summed over plaquettes, and with a coupling in front. So the coupling, now I've absorbed from here an NG. So we write a coupling, but then we absorbed in that coupling an NG from this, such that you have 1 here. I have 1 minus 1 over NG, real trace part of UP, NG being trace of the identity. And then, as we said, with sum over plaquettes. but we want to get in the continuum limit to 1 over g0 squared integral d dx 1 over 4 trace f nu squared. And if you compare these two with this, so sorry, I substitute this. So instead of this, I write this divided by ng, right? And then I identify with this. I see that the only way this is possible is if I have this identity. So beta g times, so this thing gives me a to the 4. So beta g times a to the 4 is equal to, on the other hand, I have here, so I still get 1 over 8 times what I want, so I have 2 over g0 squared. Yeah, so this was beta g over ng, a to the 4 is 2 over g0 squared times ad. So, this is a to the d. And then correspondingly, I have beta g a to the 4 minus d is 2mg over g0 squared. Okay, so we have just seen that this Wilson action in the continuum limit gives us the action for Yang-Mills theory. But the Wilson action is actually not unique. This is just the simplest action. But there are other actions that give the same Yang-Mills action with the complete continuum limit. And so being the simplest is also the one used by almost everyone, but for various reasons, also other actions appear in the literature. Okay, so we have defined the lattice action, but to formulate the gauge theory, we need to also add a path integral measure on the lattice. The measure of integration is the unique measure that is invariant on the both left and right group multiplication, meaning both u going to u times u0, so u being the link and u0 being u being the link variable, and u0 being the group, the gauge transformation, and also left multiplication, so u going to u0 times u. So that unique action is called the Haar measure. That unique measure for integration is called the Haar measure. And it has the property that is very close to the identity, meaning this du is approximately equal to, so identity meaning u is exponent I a times the gauge group A. So this is approximately 1 plus I a. And so du is product of di dA a at the point I. Sorry, at the I wrote this wrongly. well, it depends on, I suppose it depends on how you call the indices, but so the point is this index goes over over the over the dimension of the group. And then the partition function on the lattice is then the product of the integral over the product over the links of du, the link, times exponent minus SW, depending on these links. Finally, we are at the continuum limit of the lattice gauge theory. Now, the naive continuum limit would be beta g going to infinity, which is, so beta g going to infinity means g0 going to 0. So that would mean, so g0 going to 0, or beta g going to infinity would mean that there are small fluctuations around this trace UP has small fluctuations around the identity. But instead of that, we have to consider the setup that with which we began the lecture. Namely, we have to take A going to 0 while fixing some physical length psi. So that means that the continuum limit corresponds to some renormalization group equation, renormalization group-like equation. So where this physical length, let's say correlation length or something, is invariant under a change of A. Or in other way, A DDA of psi is 0. And then this, by definition, is A partial DDA minus beta, which is A DDA of G0, times partial DDG0 of psi, which depends on A and G0. All right. And the solution of this, as before, when we wrote this kind of RG equations, is that psi of A and G0 is A exponential of integral from 0 to G0 of dg over beta of G. And we also see that beta equals 0, meaning being at the fixed point, gives divergent psi's. So beta equal to 0 means this integral is infinite, exponent is infinite, therefore, and so psi is infinite. And psi is any length scale, but in particular the correlation length, which is true at the fixed point. So the fixed point, any max scale, but in particular also the correlation length is infinite. Any length scale is infinite. In a perturbative expansion, we define for beta g the coefficients. So they start at g to the third power with coefficient minus beta 0, then g to the fifth power, coefficient minus beta 1, and so on. And for SUN, we have beta 0 is 11 over third n over 16 pi squared, and beta 1 is 34 over 3 n squared over 16 pi squared. And then inputting this for SUN into this formula and doing the integration, we obtain this psi is a times beta 0 g0 squared to the power beta 1 over 2 beta 0 times the exponent 1 over 2 beta 0 g0 squared. If as a go to 0 psi is fixed, then, and since beta 0, beta 1 are just numbers, then G0 goes to 0, right? So well, so yeah, so I see here I would write this also as exponent of beta 1 over 2 beta 0 log beta 0 g0 squared, which is subleading to this thing. So this thing is leading. So so if a goes to 0, in order for this to go to infinity, we need g0 to go to 0. And if g0 goes to 0 from this definition, and then d is approximately 4, that means beta g goes to infinity. And also this relation means that there is an a of g0. So as a goes to 0, g0 goes to 0 in a particular way. It defines a of g0. And through this defines also a of beta g. So a of beta g is really what I have in this Wilson action, from this Wilson action. So a physical mass m of beta g that implies a continuum, a mass scale in the continuum limit. I mean, for something like a glue ball, so in Yang-Mills, a state of with a given mass would be a glue ball. Well, glue balls have not been observed yet, but these are have not been confirmed to be observed yet. Have been observed only on the lattice, but experimentally they are candidates, but it's not clear yet. But theoretically, we know that there should be this glue ball. So the mass, that's a physical mass in the continuum limit, and there should be some m of beta g that goes to this physical mass. Then this physical mass times psi, so then, sorry, this m of beta g times psi of beta g should be finite as beta g go to infinity. If I put a equal to 1, meaning if I consider the lattice. Okay, so this is the way one should define the continuum limit from the point of view of the lattice. You define m of beta g and psi of beta g, and as before, and then you have to consider the limit the beta g goes to infinity, and then this thing is supposed to be finite in that limit. All right. Finally, let's consider adding matter. So up to now, I described for you just the pure gauge theory, Yang-Mills theory, so the Wilson action. The Wilson action was the action for for the SUN, the action for the gauge field for the gauge group SUN. But we know that we want QCD, and that means we want things like quarks. I should therefore tell you how to put quarks on the lattice, but unfortunately the quarks are chiral fermions, fermions with chirality, with given chirality, and putting them on the lattice while keeping chiral symmetry is difficult. There are various ways to do it. People do it, but there's no perfect way, and therefore the discussion would be too long the discussion of how to put QCD on the lattice itself would be too long, and people are writing, many papers on that. So instead, I'll describe a simpler case, the case of putting scalar on the lattice, which is also a type of matter. In particular, we know there's a Higgs, and therefore this would be an application then for electroweak theory rather than QCD itself. So in that case, the scalars phi of x are in the fundamental representation of the gauge group. So for a scalar phi of x, if I discretize space into a lattice, that means I have to define it at the site I, that is, variables are phi I. And since they are in the fundamental of the gauge group, the fundamental representation, then the gauge invariance, the invariance under transformational parameter v of x, is phi going to v of x times phi. But in that case, in order to gauge invariant observable, we in the case that we have a Wilson line, so for a coupling to a gluon, this represented by Wilson line, we have to obtain a gauge invariant observable, we have to multiply with two scalars. So we know that this thing transforms this Wilson line, the path order exponential of I integral of C over C of A mu dx mu. It transforms covariantly, so transforms with v of x, v of y to the left, and v of x minus 1 to the right. And then we must multiply, therefore, with phi dagger of y, which transforms with v minus 1 of y to the right, and cancels the transformation here. And we transform with phi of x to the right, which transforms with, like here, with v of x to the left, which cancels the transformation, the v of x minus 1 from the transformation of the Wilson line. So then the discrete representative of this gauge invariant object is therefore this is phi of let's call the site I, phi dagger at the site I. Then the link corresponding to this Wilson line, uij, and then phi at site j, phi j. So this is a coupling of two scalars and something representing the gluon, or the gauge field, if you want. So, but to write an action, we also need to write a discrete version of the derivative. So I have d mu phi of x. Well, that's easy to write. we said it last time when describing Kadanoff blocking. So d mu phi of x corresponds to phi of j plus y minus phi of j plus mu, the direction mu, the nearest neighbor in the direction mu, minus phi outside j. But since we have actually the covariant derivative, and since u is approximately u is exponent I a, which is approximately, in the infinitesimal case, is 1 plus I a times gauge group capital A. So this would be d mu minus I a mu the derivative capital D mu would be this, acting on phi. So then I have d mu phi, which is phi j mu minus phi j. And then right, and then minus, so the identity here would correspond to this phi j. And then the next term would be minus I a times a mu. So up to this redefinition of a mu by little a, by the lattice size, I have just this phi j plus mu minus u j plus mu phi j. So therefore, the kinetic term, which is the modulus squared of d mu phi, is, well, sum over j and mu of this thing squared. And when I do the square and I realize that phi over j plus mu squared is the same as phi of sum over j and mu of phi j plus mu squared is the same as phi j sum over j of phi j squared, and also sum over j and mu of uj plus mu phi j, everything squared, is also the same as sum over j phi j squared. Then this thing is twice sum over j phi j squared minus, and then the cross term is non-trivial, minus 2 sum over links I and j phi I uij phi j. Okay, so so this would be the kinetic term, but then for the Higgs term, I would also need to add a mass term, which would be a coefficient times the same. Oh, yeah, sorry. Again, I do this. So this is modulus squared, and here I mean phi j dagger. Phi dagger phi, and here I also mean phi dagger I uij phi j. So it's this thing this invariant thing here, and here I have phi dagger phi. So the coefficient, so from the kinetic term I got this phi dagger phi, well, with a coefficient 2, but in some units. And then but I also need to add a mass term. So I have also a term mu, sum over I phi dagger I phi I, that includes this. And then I have this sum over links phi dagger I uj ij phi j, that's written here with another coefficient. Here is minus, so this is -2, but in general I write -k. I also have to put the real part now. The action is supposed to be real. And I also write a phi to the 4 term for the Higgs, so phi dagger I phi I squared. And then, of course, the gluon action, beta G, real part, sum of plaquettes, real part of 3 trace UP. Well, that had also, more precisely, had also, the Wilson action had also a constant part, but that is, well, I suppose that's supposed to be here as also in some sense. So this is the gauge Higgs action. We have this term that corresponds to the kinetic term. There's a mass term, there's phi 4 term, there's a gluon term. As I said, in principle, there should have been also a constant, but I'm not sure why that is not here. Yeah, I think. Well, I suppose it mattered. No. The kinetic term, the potential for the, the potential for the Higgs has also constant piece. So I think maybe the constant piece is cancelled somehow, or no, but I guess I should write in general constant piece with a coefficient still. Anyway, so that's the general action plus perhaps a constant. All right. So this was everything I wanted to tell you today. Do you have any questions? Can somebody check that you can still hear me? All right, you can still hear me, so that means you have no questions. One thing I want to observe, I had thought, at the beginning of the class, I said we'll have a final exam, but I could not think of anything reasonable way to make an exam online. I mean, the point was to have an exam in a classroom, and everybody with equivalent sets of equivalent time, equivalent everything. But online is hard to make that happen. So the only thing one can do is to do something that anyway looks like homework, to give you something to resolve in a day or so. But I don't see the point of that. I mean, that's still almost like homework. So then I decided I will just not give you a final exam and just give. I mean, just the homeworks will be the full grade, because well, it's obvious by now that in 2 weeks we will not be able to return to the IFT. So just to verify, we still have 4 more lectures. So there would be 1 lecture on Thursday at 9, then 2 lectures next week, and then 1 more lecture the Tuesday after that. So that would be everything. All right, so I will see you all next Thursday at 9. Bye.